So we will start today, inshallah, the swing equation. We'll discuss the swing equation. Most likely you discuss it in 520, and also and it's supposed to be exposed in the methods of the solution of the swing equation in terms of equal area criteria and so on. So we will go over quickly the swing equation, and then we will see the different terms of the swing equation and how to calculate mainly the electric power comes out from the synchronous generator. And we will see different types of synchronous generators and how to calculate the electrical power of each. What are the types of synchronous generators that we have in general? Does anybody know or can name the types of synchronous generator? What are the types of synchronous generators? Any answer?
I think one of them is
raising his hand, Abdurrahman Ali or Ramadan Ali, sorry.
Yes, doctor, like squirrel cage.
Okay. What else?
Brush and brushless.
طيب, any other answer, Saad Ahmed?
yes, doctor. I think permanent magnet as well. Permanent magnet synchronous generator.
طيب, let us start with the squirrel cage, Ramadan Ali. The squirrel cage is related to induction machine. When you have two types of rotors, for induction, you have squirrel cage, and you have wound rotor or a slip ring. Wound or slip ring type. So this depends on the rotor structure. I mean that this classification is based on rotor structure. Okay. So in the squirrel cage you have this is the rotor, and you have here aluminum or copper bars. Not winding, there is no winding, there is no coils, but bars. And these bars are short-circuited here, on both sides. In order, it looks like a squirrel cage, so this is why the name comes. It looks like a squirrel cage. So these are bars, aluminum bars or copper bars, and short-circuited here by slip rings. For the wound rotor, you have winding. This is the rotor, and you have phase A, phase B, and phase C, and B prime, C prime, and so on. So these are winding slots. You have here winding in these slots, and these comes out to slip rings here. You have 3 slip rings. Okay, 3 slip rings here, and these slip rings are connected to brushes. These are brushes. And these brushes here are short-circuited. Or if you want to change the characteristic of the machine, you can add here a resistor, variable resistor, rotor resistance. And this rotor resistor is varied, so you can control the torque. You can play with the characteristic of the induction motor in this case. So this is usually the torque slip characteristic, torque slip or torque speed. By controlling this resistance, the rotor resistance, you can have the maximum slip comes here. You can even have the maximum torque at starting, and you can make the motor gives you the maximum torque at starting. And the starting torque is very important, important specification for the induction motor. You know, if the load torque is below the motor torque, in this case the motor will not start. If this is the load torque, that's okay. The starting torque is higher than the load torque, it will go. But if the torque here, if the load torque is here, so these two motors will not be able to start the motion. So you can play with this resistor in order to have a starting torque very high, so you can go. So this is the classification of induction. And I'm asking about the synchronous. Synchronous, we have similar classification. We have what we call cylindrical or round rotor. In round rotor, you have a rotor, you have winding, slots, and winding, and so on. So these slots represent, or you have the coils here, and this coil represent, for example, North Pole, and this is South Pole, and this is North Pole, and this is South Pole. So the poles here are distributed poles, comes from the coils. The other type is what we call salient pole. Salient pole type, where you have the rotor is the poles here are salient, بارزة, أقطاب بارزة. So you have here a coil here to represent this is north and this is south, this is north and this is south. So this is the rotor. So salient pole. The poles here are salient. طبعا here الروتر is round rotor, وبالتالي الاير جاب here is regular, symmetrical throughout the rotor, but here the air gap is different. You have here high air gap. طبعا of course the stator is there, and this is the stator. So this is the air gap here. This is the pole and this is the stator. So this is the air gap, but here you can see the air gap is longer and so on. So you have here irregular air gap in the salient pole. This type, of course, you can have permanent magnet, definitely, yes. You can have permanent magnet. So instead of having a coil here supplied by a DC supply through brushes and so on, you can have a permanent magnet pole here. This is okay. This could be, if you want to have it here as a third. But in terms of the structure of the rotor, is you have a round rotor and you have salient pole. What is the application of this one? What is the application of this one? In which application you can have the round rotor? Or what is the specification of this round rotor? What are the characteristics? What are the characteristics of this round rotor type? Any clue? Any answer? This type is characterized by number of poles is limited. And in this type, number of B poles 2 or 4. 2 or 4. And in this case, the synchronous speed is high. Ns equal to 120 F over B. Now the frequency 60 Hertz, and this is number of poles equal to 2, but you have 3600 RPM. Now this is 4 by 1800 RPM. This is, the speed is high. But here you can have like number of poles. You can have it 4, 6, 10, 12, 16, whatever. You can have here a high number of poles, and the synchronous speed is limited. So this type is more suitable to hydro power plant. Hydro plant. And the speed of the rotation here is very, very, very slow. The hydro turbine is very slow, but this one is used for thermal power plant. Thermal power plant. So the speed here is high, and so on. So these are the two types of synchronous generators. طبعا the stator on both types are the same, 3-phase winding. This is the stator. So how to calculate the electric power output of this type of the synchronous machine, which is widely used here in Saudi Arabia. طبعا we don't have hydro plants, so this type is not there here in Saudi Arabia. How to calculate the electric power output of this, and also of this type of the machine. Any question?
Yes,
Yes, please. Ahmed Suleiman, you go ahead.
what happens if the salient pole generators, what happens if they are used in the same power plant? What will happen? Will it be an advantage?
Your voice is not clear, ya Omar. And try to, and I couldn't hear anybody.
What will happen if the salient pole generators, okay, is allowed to be run with the same power? Will it not be an advantage?
If the salient pole generator operates
With same power plant?
with thermal power plant,
Yes.
لا, it is not happen as such. يعني you cannot, if the generator is designed for a specific speed. So we have some mechanical design, mechanical structure in order to be suitable for a certain speed. You cannot take a generator designed for 300 RPM synchronous speed and you put it in thermal power plant with 3,600 RPM. So this is did you get the point?
Yes.
Yeah. it is not interchangeable. طبعا the generator is a very huge component in power system, very expensive component. It is designed for a specific plant, but you cannot switch definitely. Okay, so we will go over the time scale of power system studies. we pointed out to this time frames of each study in power system, like lightning, transient stability, voltage stability, load flow, and so on. So in order to highlight what is the time frame that we are interested in. The stability definitions, we have three types of stability, as we mentioned earlier. So steady-state stability, dynamic stability, and transient stability. And this classification is based on the severity of the disturbance. You have a disturbance, how much the severity of the disturbance. And also the time frame is different. Time frame for this one, you can have it longer time. This is somehow a few cycles up to few seconds, but this is maybe few cycles after the disturbance. Details of the modeling also is different from one type to another, and this is what we will discuss here. Then we will derive the swing equation, and we will see the components and how to calculate the electrical power in case of cylindrical rotor or round rotor synchronous generator, and also in case of salient pole synchronous generator. Okay. So as we mentioned earlier, dynamics of the power system comes from the load changes, generation changes, and also switching and lightning, faults, and so on. All these are the disturbances happens in the power system. So the time frame of each one, or the speed of occurrence, you can see it here. I don't know, do you see the last row or not? But let us see here lightning surges. This is nanoseconds to milliseconds, switching surges, harmonics, subsynchronous resonance, transient stability, dynamic stability. These are the area of interest in this course. We are interested in dynamic and transient stability, where the time frame is millisecond, 10 millisecond to 10 second. 10 millisecond, roughly speaking, these are not the hard limits. This is 10 millisecond means about half cycle after the disturbance. If the cycle is 16 millisecond, 16.67 millisecond, so we are interested in 10 millisecond. Maybe half cycles or one cycle after the disturbance, what is the performance of the power system? And we can judge whether the system will be stable or not if we study the response in this time frame for transient stability up to 1 second, up to 60 cycles. For dynamic stability, the time frame is a little bit higher, from 0.1 second and 100 millisecond, 6 cycles up to 10 seconds, and you can have 600 cycles. So these are the time that we are interested in. And definitely, if we are talking about this time frame, so we will not be interested in lightning surges and switching surges and all this, and also in the other types here, which is the steady state, comes to a steady state like a load flow or something like this. So this is the time frame comes to 1000 seconds, and it becomes 6 minutes or so, more than 6 minutes, definitely about 6 minutes, 360 seconds. So about 18 minutes. Oh, this is the steady state phenomena here. This is the almost steady state. And حتى power flow, if you still remember, the power flow is characterized by algebraic equation or a differential equation. The power flow problem, load flow or power flow. What do you think? Do we have differential equation or algebraic equation there?
For the power, it's algebraic equations.
Algebraic equation, nonlinear algebraic equation, and solved by iterative methods, which is Newton-Raphson or Gauss-Seidel. So algebraic equation, and there is no dynamics. Dynamics means you have a differential equation. Something varies with the time. You have dx by dt. So this is the dynamics here. For this very fast dynamics, you need to represent the system by partial differential equation. And you have derivative with respect to time and also with respect to distance. So you have your partial differential equation to characterize this one. And then for the slower phenomena, such as gradual change and generation changes, gradual load and generation changes are modeled by lumped parameters. حتى هنا في distributed parameters. And you cannot lump the transmission line by replacing it by one resistance and one reactance. And you can lump the capacitor at both ends. You can use by no. And these are distributed parameters here. So here are the lumped parameters, and you can have algebraic equations and also differential equations. It depends on where you are targeting, which study you are involved in. So we will see the three types of stability: steady state, dynamic, and transient stability. As we mentioned, this classification is based on the severity of the disturbance, and based on the severity of the disturbance, we will see how to model the system in case of steady state or dynamic or transient stability. So the stability definition in general, whether it is steady state or dynamic or transient, in general, the stability is defined as the ability of power system or power system machines or generators in the power system to be in the synchronism, to be kept in synchronism. All the synchronous machines are moving together. You have like a stable frequency, stable speed of each machine. So the machines are stayed in synchronism, and if you have a disturbance, the machine will reach to equilibrium point, to steady state value, and stay there. Even if the frequency is less than 60 hertz, it doesn't matter, but this can be, an action can be taken later, but the machines are running together in synchronism, the same frequency, same speed for all the machines. So this is the stability definition in general, and the stability studies may be classified upon the nature of the disturbance as follows: the three three types of stability as we mentioned earlier. And steady state stability is defined as, refers to the ability of the various machines in the system to remain in synchronism. Up to this point, this is the general definition of the stability. Here the characterize the steady state stability in the small and slow disturbance. Very small disturbance and very slow. And time is not a big deal here. Like a gradual change in load. You have a gradual change in load. This is if you want to check the stability after this disturbance. This disturbance is small and slow, so you are talking about steady state stability of the system. So the characterization of the system here is a very simple synchronous machine model can be used. And you can have generators treated as a constant voltage source behind the reactance, similar to what you are taking in undergraduate. This is the synchronous machine representation. So maybe you have here RA, armature resistance, synchronous reactance, and you have here the internal voltage or the induced voltage, and this is delta, and this is the terminal voltage, and you have here the current I, armature current. So you have here voltage source behind an impedance or behind the reactance. So this is the representation of synchronous machine. Definitely this is not the case if we have a big disturbance. We cannot simulate the system as such. We have to have some differential equations and representation we will be discussed in details later on at certain parts of this course. So this is the simple representation of synchronous machine. If you have gradual change in the load. In addition, this kind of stability studies is usually analyzed by load flow to check the phase angle and the bus voltages. Usually, if you look at the load flow results, and here load flow results, what is the output of the load flow program? What is the output? Any answer, Muhammad Taghi sir? What is the output?
Voltage, angle, reactive power, active power.
Okay, well, so if you have the voltages here and the angles and whatever here, you can look at the load flow solution and you can evaluate whether this system is stable or not. Not only that, but you can also judge whether the system is strongly stable or close to instability. And where are you from the limit of stability? From where we can extract such information? From where? If you have such output. Abdulaziz Khalid?
Sector, mainly the voltage. For example, if the voltage is less than 0.85 per unit, it indicates the system is unstable.
Are you talking about angular stability or voltage stability, Abdulaziz?
Voltage stability.
Okay, voltage stability, you can see the voltage profile and you can judge. Now from the angle stability, which information you need to look at? Abdulaziz, are you looking at the voltage or looking at the angles?
I thought your question was about the load flow, how to determine if the system is stable from the load flow solution.
أيوة ما هو الستيبل ديت الستابيليتي has different meanings or not different meaning, but you have different kind of stability in the system. You have angular stability, you have voltage stability, and you have frequency stability, right? We
Yes.
classify stability at the beginning as such. So looking at the voltage, or if you want to examine the voltage stability, okay? Although This could be misleading, by the way, Abdulaziz. يعني usually الفولتج بروفايل يعني انت ممكن هنا في السيستم in your system you can find this as 1.01, 1.0.995 and all the voltage are very close to 1. But unfortunately the system is very close to instability. Look at this curve. احنا قلنا في الفولتج stability we plot the voltage versus the real power, right? Is it clear?
Yes.
So maybe the voltage is not reducing as much, but the voltage could be going as such, and then you have, although the voltage here is very close to 1, but you are also very close to instability. And usually the voltage profile, and this is in general, the voltage profile doesn't reflect the voltage stability. Okay? And as we mentioned, you can see the voltage profile here is very close to 1. Everything is fine, but you are very close also to instability here. For voltage stability, you look at the voltage, okay, no problem. حتى هو leading ولا misleading, whatever it is. يعني, but for angular stability, you look at the angles. You know the power between V1 with angle delta 1, V2 with angle delta 2. How much the power B12? B12. How much of the power through this line? You have here a bus V1 with angle delta 1 and V2 angle.
V1 minus V2 multiplied by the conjugate of, okay, this, and okay.
V12 equal to V1, V2 magnitudes over the reactance of the line, neglecting the resistance, sine the angle difference, delta 1 minus delta 2. So you can come here. What is the maximum power that can be transferred through the line? When it comes, usually when this equal to 90 degrees.
90 degrees, yes.
So if you have the difference, and you can see here the maximum difference between these angles, or you can see for each line what is the maximum difference for this line. Is it 20 degrees, 30 degrees? If you have 20 degrees, so this is B delta curve. This is B delta curve, sinusoidal as such. So if the angle difference is 20 degrees, so you are here. You are very far from the limit of stability. If the angle difference is 30 degrees, you are here. In 80 degrees, you are here. 90 degrees, you are at the limit of stability. So you can, from the load flow, for this steady state stability, you can check it from the load flow results. You can look at the angles and see the difference of the angles. What is the range of the angle differences? What is the maximum difference that we have here? So you can look at this and see, and for 20 degrees, the maximum, so the angle, the system will be strongly stable. You're still far from 90 degrees. Is it clear?
Yes. Thank you, Doctor.
So, any question? Okay. So in general,
Doctor.
yes.
Please, just before we leave the definition of stability, I observed that the definition of stability is defined in terms of machines synchronism. So does it mean that we do not have instability where we have just one machine, we have only one, maybe only big generator, thermal generator that is serving a particular process?
Omar, Your voice is not clear. Try to fix this problem.
Okay.
Okay. As I understand from your question, and no, if we have one machine is out of synchronism.
If you have only one machine that is powering a particular network, maybe we have just a very big machine that is powering the whole load in a network. Can't we have instability in such case?
Of course, if you have some measures to isolate this machine and you keep the system running in synchronism, so this is you have to have some measures in this case. Now, if you keep the machine which is out of synchronism running in the system, so definitely the system will be unstable.
Doctor,
Yes.
what I'm saying is that in a particular power network, we only have one machine. I mean, we don't have machines synchronized together. Only one machine. Maybe a very big power machine, power station that is only one machine that is powering your network. Can we talk about instability of this type in such case?
Are you going to keep this machine running, or you will isolate it?
Running.
Running with out of synchronism?
Yes, because only it's only that machine. We don't have another, only one machine that is running. We have only one generator, just one generator that is serving a whole network. But the generator is very big, so we don't have others connected together. Only one. I'm saying that can this kind of problem of instability occur in such case of one generator?
Well, look, Omar,
No.
we cannot keep the machine running out of synchronism. Out of synchronism means the system, the generator can be a motor at a certain time and absorb power. And the currents will be very high. The current depends on the angles. So if you have the angle is negative and the angle of that bus or the system is positive, so that means a huge current will damage your generator. The generator, you have to isolate it. The protection must isolate this machine which is out of synchronism. You can have directional power flow, directional relay to prevent the generator to become a motor if it runs out of synchronism. Okay? So you need to keep your generator intact. You don't want to damage your generator. If you keep it running out of synchronism, your generator will be damaged. Okay?
Okay.
So this is the point. You cannot keep the generator running out of synchronism and you can say, no, this is a small generator, so it will not affect the system. Yes, it is a small generator, it will not affect, but it will damage. Okay, you have, when you have this out of synchronism means what? Out of synchronism means this is the delta and this is the time. So the machine is running here at delta 0. And if the fault occurs here somewhere and the angle start increasing monotonously, so the angle or it comes down here and ups and downs and so on. So in this case, the angle is changing. So at a certain time, the generator becomes a motor and absorb a huge current. So it will be damaged. Okay?
Okay, doctor, thank you.
Okay. So this is the steady state stability from the load flow. You can judge load flow is algebraic equation. You can use the system modeling here is algebraic equation, and you can see the maximum difference of the angle, and you can see this. Okay. Dynamic stability refers to the ability of the various machines in the system to remain in synchronism. This is again, up to this point, this is the general definition of the stability. Here, the specification of the dynamic stability. After a relatively small and sudden disturbance, there it was a slow disturbance, we have here sudden disturbance, and still small but sudden, such as badly set of automatic controls. You have you change of the V reference in automatic voltage regulator. For example, automatic voltage regulator is you have here the terminal voltage, V terminal, and you have here V reference, and the error goes to the the excitation, which produce flux here, the generator stator. Okay. So if badly or suddenly you have some disturbance here in V reference. V reference was 1.0 and it goes to 1.1. And maybe due to the necessity of the power system operation, you need to increase the terminal voltage of the generator. انت لو عندك voltage problem, if you have low voltage at a certain buses, one way to adjust the voltage is to increase the V reference of the generator, right? طبعا you have also the transformer tabs, you have the shunt compensation in terms of capacitors or static voltage static var compensator or statcom or whatever, or synchronous condenser. You can have other types, of course, of solution, but one solution to solve the low voltage at a certain buses, you increase the VG, generator voltage. The voltage here is 1 per unit. Okay, that's fine, 13.8 kilovolt. Now we have low, we experience a high load, and this high load will reduce or will decrease the voltage, and we need to regain the voltage back to its normal state. So we can increase the terminal voltage here by 1.1. So we have a steady change here in reference in order to adjust this voltage. So this is some kind of sudden change, small change but sudden. In this case, we are working on dynamic stability. And in the dynamic stability, the excitation system and the turbine governing system are represented along with the synchronous machine models by linear differential equations. We have here differential equations, but you can linearize these differential equations. You can linearize these differential equations. You know, a small change. So this is, we can linearize, but it is differential equations. The system can be stabilized by linear or continuous supplementary control. You have power system stabilizer, you have a governor, automatic voltage regulator. So all these controllers will help in solving the stability problem here for dynamic stability. For dynamic stability also, the nonlinear differential equation and the algebraic equations can be replaced by a set of linearized equations, as we mentioned. You can linearize the equations. The equations are nonlinear. Usually, we have nonlinearity. From where comes the nonlinearity? And we have here V equal to V1, V2 over X12 sine delta, or delta difference, delta 1, 2. So this equation is linear or non-linear?
Non-linear.
Non-linearity comes from where? Non-linearity.
Sine equation.
And there,
From the sine term. Okay, so this system is this equation is nonlinear, and if you are talking about small disturbance, you can linearize it. You can assume that this delta is changing to delta 0 plus delta delta, and you can start expanding and you start to do some approximation and so on. So you can linearize the equations here in dynamic stability. So the solution technique is to examine the stability of the system under incremental variation about the equilibrium point. Here, if the delta becomes delta 0, this is the equilibrium point. This is the initial steady state point, plus this incremental change in delta. And you can check whether the system will be stable or not if we have a small change in this delta. So this is called dynamic stability. Transient stability, again, general definition, ability of the various machines in the system to remain in synchronism here. Up to this point, this is a general definition. What characterizes the transient stability from dynamic and steady state is sudden and large disturbance, such as sudden change in load, fault, loss of a generator, switching operation. These are severe disturbances. Sudden and large, this is the characterization. هناك كان small and sudden for the dynamic stability, and for the steady state, it was for the steady state stability, it was what? The disturbance. Small and slow. For dynamic, small and sudden. Here for the transient stability, the disturbance is sudden and large, or large and sudden. So if you have sudden change in load, and you have a big industrial plant, and you switch it on or you switch it off suddenly, so this can create a problem, stability problem to the power system. And you are talking about مثلا very huge load. Very huge load, if you are talking about مثلا حديد مثلا, شركة حديد company. They have 6 furnaces. And each furnace is 150 megawatt. 6 furnaces, and each one is 150 megawatt. One furnace is 150 megawatt. So such load, such industrial load is very huge. If you switch the furnaces on suddenly, you can create a stability problem to the system. So you have to, of course, this is 6 times 150, and you are talking about 900 megawatt. 900 megawatt, almost one plant. Okay, and maybe half of the plant, to only one load. So this is very big load, and they have to, what we have learned. I have a chance to visit Hadid and see this, and they said that we have to communicate with the Saudi Electricity Company about the scheduling of these furnaces. So the power system operator here should be aware about the time when they switch on the furnaces. So he has to have like a spinning reserve to cover this. Otherwise, the system will be in trouble. So sudden change in load, big loads, fault, three-phase fault or single phase or whatever, any type of fault, this also a big disturbance and sudden. Loss of a generator, of course, this will create imbalance between the load and generator, and you have a switching operation. If you have one line is out or so, so in this case also this will disturb your system. So these are the disturbances. Under these disturbances, you are talking about transient stability in this case. So such disturbances are beyond the capability of the linear. Now, sudden and big, you cannot linearize. You cannot linearize the equations here. So the equations will be nonlinear equations, differential equations, and maybe continuous supplementary control. Yani beyond continuous supplementary control, you may need here some aggressive actions and discontinuous or discrete actions on the control. And as you, if you still remember, we pointed out before, in one way to, if you have some kind of frequencies increasing, you may need to a dummy load or braking resistor, and this braking resistors are switched on and off in a discrete fashion. So in this case, the system here, or the measures, will not be a continuous measures, but very aggressive on and off. So in this case, the capability, beyond the capability of linear and continuous, the system may lose its stability at the first swing. Yani after few milliseconds after the disturbance. So you are very much interested in the first swing of delta versus T. So you look at this is delta 0, fault occurs here. So this is the first swing. If the system come back, if the system of the angle here comes back, we can say the system is stable in the first swing. If the system is unstable, then the angle will increase continuously. But if the angle comes back, we have a hope, some controls, some actions can improve the situation. So you need to check the stability, maybe in the first swing or multi-swing, and you can have, again, so if you increase the time, time of the study, so you can see whether the system will be stable or not. Then maybe first swing could be stable, but due to lack of the damping, the system will, the oscillation will increase, and the system eventually will be unstable. So the system may lose its stability at the first swing unless a more effective countermeasure is taken, usually the discrete type, such as we mentioned earlier, we have dynamic resistance braking, or we have fast valving, and you can decrease the valve opening of the steam very fast, or you can have some load shedding. You need to disconnect some loads if the frequency is going down. Is it clear? Okay. So the nonlinear differential equations and the algebraic equation do not allow the linearization. We are not talking about linearized model here. And this of the response can be evaluated using the iterative step-by-step procedure, or what we call the numerical integration, like Euler method, trapezoidal, and others. Transient stability problems can be subdivided into first swing, which is based on a simple generator model, and the multi-swing. In multi-swing, some controllers can take an action. You can have, like, generator control systems, governors, bar system stabilizer, exciter, what we call regulator. All these will help. Okay, if the time frame is longer, and the effect of these devices is not a sudden change, but it takes time, as we will see later on, the time constants of the turbine, time constant of the automatic voltage regulator, and all these issues. So the period under investigation can vary from a fraction of the second, the first swing, okay, fraction of the second, to 10 seconds for multi-swing case. The time frame definitely is longer in case of multi-swing. And I would like you to open the blackboard, and you will see a very simple quiz, multiple choice quiz. So will appear at some time, maybe after 5 minutes or so. And in this case, you can take about 3 minutes to solve the quiz. Okay. So be ready. It will appear after some time. Is it clear?
Yes, Doctor.
Okay.
Doctor,
Yes.
is this
I couldn't hear you, Ramadan.
Yes.
What's your question?
The quiz will be weighted part of the grading.
Yes, it will. And it will have a very small weight, but it's very straightforward. And maybe the quiz, such quizzes will not help only in evaluating the your background or your study or whatever, but it also helps in other ways. Be ready, open the blackboard. It will appear in a sudden for 2-3 minutes. You can solve even less, and definitely it will be a straightforward question. Okay, so let us continue. So the swing equation. So you can see here the balance swing. Here is the balance swing. So what do you think this one, what do you think this one for the bar system? What is this and what is this? And if you want to apply this to the bar system, this represents what and this represents what?
Be mechanical and be electric.
Yes, you are right. This represents the generation, and this represents the load. So you have to have a balance between the generator and load. If you don't have a balance, then you can see the system oscillating, the frequency is oscillating, and so on. So this is The swing equation is, it mimics what we have in balance swing here between generation and load. Okay. This is an equation relating the rotational masses to the generator electrical parameters. You have here the mechanical power or mechanical torque comes from the turbine here. And this is the inertia of the generator rotor. And this is the electrical power or electrical torque output, which is converted to current and voltage here. So you have here B mechanical input, B electrical output, and you have the speed here, which is the in normal cases, at steady state, this is synchronous speed. So this is the equation of the motion of any rotating mass. If this is a rotating mass, has an inertia J, J times the acceleration d square theta by dt square, or d omega by dt, or alpha here, J alpha, acceleration, equal to the accelerating torque. This is accelerating torque, which is the difference between the input and the output, T mechanical minus T electrical. So we can have here J is the moment of inertia of the rotating mass, theta the angular displacement of the rotor with respect to the stationary axis in mechanical radians, and the T is the time in second, Tm the mechanical torque, T is the electrical torque, and the TA is the accelerating torque. So this is generally the equation of motion of any rotating mass. But here, this mechanical displacement or angle or the this we need to express it in terms of electrical angle. So we will see how to transform this mechanical angle theta m to electrical angle, which is delta or theta e. So now for this equation, if you want to analyze this one, if the acceleration torque is 0, T mechanical equal to T electrical, or B mechanical equal to B electrical. If this is 0, that means there is no acceleration. The acceleration is 0, and the speed is constant. So the machine is running at synchronous speed. The machine is constant. Okay, so if TA is greater than 0, what will happen if TA is greater than 0? What do you think? Any clue? Any clue? Any answer? Any answer?
That means the mechanical torque is more than the electrical torque.
What does it mean in terms of acceleration or deceleration?
It is accelerated.
We have acceleration, and the speed will go up or down.
Will go up.
The speed will go up. Yes, you are right. So if the quiz is running now, do you see the quiz?
Yes, I do see the quiz.
Okay, please go and answer it. 3 minutes, you have 3 minutes. 3 questions, by the way. We have some of you not started yet. Ahmed Saad. Ahmed Al-Gannas.
Exist.
There is a quiz. You have to answer it. The Zaid Abdullah. Dahi. Mahmoud.
Dr. I can't find. Is it on the blackboard?
As we mentioned, we have a quiz on Blackboard, so please go and do it. Okay, so let us continue. So if TA is greater than 0, then this term will be positive, and we have acceleration. Acceleration is positive, so that means that the speed is going up. The frequency is increasing, and the speed is increasing. And the opposite way, if we have the electrical torque or the load is higher than the input power, mechanical power. So in this case, the acceleration torque would be negative. That means we have here deceleration. The angle is decreasing, the speed is decreasing, and the frequency is decreasing. So this will be the three cases that we have here. Okay. So you can define, of course, we need to convert the mechanical angle to electrical angle, to delta E, حتى even not delta M. So you can define theta M equal to omega S mechanical times T plus delta M plus a displacement from the synchronously rotating frame or reference. So this is theta M. Theta M, omega is the synchronous speed of the machine in mechanical radian per second. So delta M is the angular displacement of the rotor from synchronously rotating reference in mechanical radians. So I hope you can have here some kind of illustration, and you can see here if this phasor, if this is the phasor and rotating, this is the angle here, theta M. This is stationary frame or stationary reference, fixed angle. So if the speed here is omega, the rotating speed here is omega. Okay, so what is the angle after some time? What is this angle after some time? Okay, so this is the angle here. You are measuring this angle. So the displacement here equal to this angle, which is the originally shift from here, plus omega S times T, load time. So you have the displacement here, the angular displacement, plus the angle here. So if you relate this angle not to stationary reference, but to synchronously rotating reference. So if you relate it to synchronously rotating reference, in this case you can write, of course this is just a derivative of the previous equation, d theta by dt equal to omega plus d delta by dt. So d square theta by dt square, this is constant speed, so this will eliminate or diminish, and then you have d square delta by dt square. So in the swing equation, you can replace d square theta m by dt square by d square delta by dt square. This is still mechanical angle. Okay, now we need to replace this by electrical angle. What is the difference between the mechanical angle and the electrical angle? Does anybody know what is the difference between theta mechanical and theta electrical, corresponding theta electrical? Yani if you have theta mechanical, can you get how much theta electrical corresponding to it? Let me show you one thing. If this is the 2 poles here or 4 poles, these are 4 poles. Okay, this is north, south, north, south. If you have a conductor here and you want, this is a conductor, and you want to plot the the waveform of the voltage induced if this is rotating. If these are rotating, can you plot the waveform of voltage induced here in the conductor? Can you do it? What is the waveform here?
Sorry.
The complete cycle here represents 360 degrees electrical. Okay, this one. طيب, for this positive part, this pole, assume it is under north here. When it comes to under south pole, it will be negative here. Right? Is it clear?
Yes.
So with one, and then you have a north and then south, so you have another cycle here. And this represents a half cycle of the rotation here. This half cycle is 180 degrees mechanical, but in electrical it is 360 degrees, يعني double. يعني the conversion between the mechanical angle and the electrical angle is related to the number of poles, or specifically number of pair of poles. Number of pair of poles. How many pair of poles here we have? How many pair of poles here?
Two.
Two. So the theta electrical equal to a number of pair of poles times the theta mechanical. So for complete cycle here, which is 360 degrees mechanical, we will have here about 720 degree electrical, two complete cycles of the sinusoidal waveform. So theta electrical equal to theta mechanical multiplied by a number of pair poles, or theta mechanical equal to theta electrical over a number of pair of poles. So this is the relation between the mechanical angle and the electrical angle, and I think the time is over. So let us stop here and continue next class, inshallah. If you have any question, you need to discuss something, so you can continue with us. And if you don't have any, so you can simply leave the meeting.
Okay, thank you, Dr.
Okay. Thanks.
Thank you.
Thank you.
Thank you.
Thanks. Assalam.
Assalam.
Assalam.